Hello everyone, welcome to the lecture on uncertainty modeling in AI. And today we are at our last lecture where I will talk about the graph cut and alpha expansion algorithm. Specifically, I'll talk about the max flow mean cut algorithm, which is commonly used for discrete optimization, and I'll show the relation between the max flow mean cut algorithm and probabilistic inference. Of course, I didn't invent any of today's material. I took a lot of slides and content of today's lecture from the textbook written by Simon Prince. Although this is a textbook written for computer vision, it contains a very detailed description of graph cut and the relation between the max flow mean cut algorithm with probabilistic inference. I also took some slides from this lecture by Princeton University on max flow mean cuts, and I also took some of the reference from the original paper which relates the max flow mean cut algorithm with probabilistic graphical inference for computer vision. I strongly encourage every one of you to take a look at all these three reference materials after today's lecture. Hopefully, by the end of today's lecture, you'll be able to convert the binary or multi-labeling problem into a max flow mean cut problem. And then we'll be able to solve the max flow mean cut problem using the augmented path algorithm, which I will talk about in detail later. You should also be able to explain the concept of submodularity, and we will look at how to solve the submodular binary or multi-labeling problem with max flow mean cut algorithm, and the non-submodular multi-labeling problem with what we call the alpha expansion algorithm. Now, in the earlier lectures, we have looked at the case where we saw that if given a latent random variable that gives rise to an observation over here, which we call xn and zn respectively, if all these latent random variables are independent of each other, then we will make use of the mixture model to represent this particular graphical model and to do inference with the expectation maximization algorithm. We saw that the difficulty of the problem increases if there is a linear relation. This means that in this particular case here, we have zn minus 1 that is influencing the results of, or the states of zn over here, and both of them respectively has an observation of xn minus 1 as well as xn, and this could form a linear chain or a linear hidden Markov chain that we see that in this particular case the inference can still be done in exact form using the expectation maximization algorithm, but it becomes much more complicated than the mixture of model inference. And in this case, we will need to do the forward-backward algorithm, which is much more tedious. And we also saw the two of these cases, they are all belonging to the case of exact inference, where we can do inference in a exact message passing manner. But we gradually proceed on to look at the case where if all the hidden latent random variables are very strongly or linked in a way of in a loopy manner, as this example over here, where each one of these would also have a observed random variable which we call xn over here. And in this particular case, we saw that it becomes intractable to do the inference. And in the previous lectures, we look at two methods of doing approximate inference over here. So in this case over here, we'll do what we call the approximate inference, where we look at two particular cases. The first case would be the stochastic proximate inference, or the MCMC algorithm that we look at. And the second way would be to do the deterministic way of the inference. In particular, we look at the variational inference approach to do the approximate inference over here. So notice that in all these three general graphical model, there is a similarity where the smallest unit is always made up of a latent random variable z pointing towards an observed random variable in all these three examples over here. We saw that the difficulty arises because of the relations or the links between the latent random variable, and when it forms complicated loops like this, then exact inference becomes impossible, and we have to rely on approximate inference to do the to infer this particular graphical model. So approximate inference means that the solution won't be exact over here. We won't be able to get an exact closed form analytical solution or an exact form of solution. It will be just an approximate form of the solution. So the question here is that, can we actually do better than approximate inference? Could there be some cases of this kind of graphical model, which is actually illustrated by this example over here, where I'm going to, for every pixel in my image, I'm going to label whether it's taking one out of k classes. And now the question is that, is this particular pixel going to be water or the sky? And we saw that this can actually be done using the variational inference or the MCMC algorithm. But both these inferences are approximate. And today's lecture, we will ask ourselves whether can we do better than approximate inference, where could there be some cases in this particular graphical model where we can actually do exact inference, even though the graphical model is a loopy one. So the question is that, can we do better than approximate inference? The answer turns out to be yes, and there are actually three cases of this particular problem, which we call, or the solution, which we call the graph cuts. It depends on the Markov random field type. This means that in our graphical model that looks like this with a loopy latent random variable, as I have drawn in the previous slide. And in this particular case here, we'll see that if the Markov random field type, it's a binary label. This means that all the latent random variable, which I generally call Zn, it's going to take a state of 0 or 1, a binary state. And we will see that if it is the cost function, this means that the potential between Zi and Zj, where both of them are neighbors, forms what we call a submodular cost. We'll look at this, the definition of the submodularity, in more detail later on in the lecture. But for now, let's treat this as a term over here, where assuming that this submodularity is true in the cost function, then together with the binary type latent random variable, then we will see that exact inference on this particular graphical model would be possible. In the second case over here, even if this Zn here is going to take multi-label, this means that in this case it's going to take one out of the k classes that we are interested in, and as well as the cost. This means that the pairwise and the unary cost function over here, they're all going to form a submodular cost. Then we'll also see that exact inference is possible. We'll not only see that this exact inference is possible, we'll also see how to actually execute this particular algorithm to do inference, to do exact inference for this type of graphical model under these settings. And we'll also see that in the case of a multi-labeling problem where Zn here is going to take one out of k classes, but in this case here, in the third case here, we're assuming that the cost, the pairwise cost and the unary cost, they are non-submodular. Then we will see that it's going to, we are still able to do the inference, whereas exact inference would not be possible anymore. We will have to resort to what we call the approximate inference, and we'll also see that this will only exist for some cases. This means that some of the cases that falls under this category would be so hard that it's impossible to solve. And we'll in today's lecture, we'll see that these two can be solved using the max flow mean cut algorithm. And in this as approximate inference, we'll see that this can be solved using the alpha expansion algorithm. Now, one of the examples that we have seen in the previous lecture, where it can be modeled using the graphical model, the Loopy graphical model that we have seen earlier, that looks like this, the grid-like graphical model. where all the latent random variable forms loopy grids that look something like this. So more specifically, the image denoising problem can be used to illustrate the binary and the multi-labeling task. So on the binary level, here's an example. Given an image that looks something like this, where it's actually corrupted with binary noise, where every one of these pixels is randomly flipped from between 0 and 1. If it is 0, then it's completely white, and if it is 1, then it's completely red in this particular example over here. And the task is that given this particular image that is corrupted with noise randomly, we want to recover the clean image over here, and this would be the binary image denoising problem. And we'll see that we can actually solve this particular problem using the graph cut algorithm. And here's another example where it's a multi-labeling task, where given an image that is a grayscale image that looks something like this, which is corrupted with also noise over here, where the values of each pixel is randomly changed from 0 to 255, because this is a grayscale image. And the idea here is that given this particular corrupted image, we want to recover the clean image, the multi-scale image, using the graph cut algorithm. So as I've mentioned, given the noisy observed data, which we are going to denote as x, where I have all the pixels denoted as x1, x2, all the way to xn, so there are altogether n number of pixels in this particular image over here. The goal now is to recover the uncorrupted image, which I represent every pixel in the uncorrupted image over here as w1 all the way to wn. Now we can see that from the problem formulation, it becomes apparent that this w over here, which is the uncorrupted image, is what we want to recover, and this is also the set of latent random variable that we are interested in, because this is unknown to us, and given the image over here, all the pixels which is noisy over here, we want to recover this particular uncorrupted image, which is treated as our latent random variable. So this means that the observed data over here, all the pixels over here, are going to be our observed random variable in our graphical model. So what this means here is that every one of this particular pixel in our uncorrupted image is represented with a latent random variable, which we denote as w1 to wn over here. And what's interesting here is that we can also add on some prior knowledge that we want neighboring pixels to be as smooth as possible. This means that there will be a constraint between all the neighboring pixels over here, or at least the 8 nearest neighbors in this grid structure over here. And for each one of these latent random variable, which is the uncorrupted image that we want to recover, there is an associated corrupted pixel in this particular observed data over here, which we are going to denote as x. And what this means is that if we were to put both of them together, for each one of these latent random variable, I'm going to have a corrupted pixel on the observed data over here, which I'm going to denote this as w1 and this as x1, and so on and so forth over here. So we can see that this becomes obvious that it's going to form this graphical model over here, which is the Loopy graphical model that I have mentioned earlier in the start of the lecture. Here, note that because I took this particular figure from the textbook written by Simon Prince, Computer Vision, and the notation here is slightly different from the Christopher Bishop's textbook, which I have followed for most of the lectures. In the case of the Christopher Bishop notation, all the observed random variable should be shaded. And here what this means is that all these random variable that represents the observed data should be shaded over here to be more consistent with the representation that is from Christopher Bishop's textbook. What we can see here is that the final graphical model here ends up to be a Markov random field, where each one of these latent random variable over here is linked to its 4 closest neighbor, and we want to make use of this to enforce the pairwise smoothness prior in the uncorrupted image. What this means is that for each one of the pixel that I'm looking at in the uncorrupted image that is represented by my latent random variable, it better take the same state as 4 nearest neighbor here. This is because of our prior knowledge that in most naturally occurring images, the neighboring pixels are more likely to take a same state. So more formally, the posterior distribution of the Markov random field is given by this expression over here, where we express the latent random variable condition upon all the observed random variable, and this will lead to us to the probability distribution, the posterior probability distribution of P W1 to Wn conditional upon x1 to xn. By applying Bayes' rule over here, where we flip x and w to becomes the likelihood term over here, where we now get x condition upon w and a prior term of our latent random variable over here, which is given by P of w1 to wn divided by the normalizing constant. We can further see from the graphical model that the likelihood term, which is supposed to be written in this particular way, 1 to n condition upon w1 all the way to wn over here, it's independent of each other, because we can see that there's no link between x1 to all the other observed random variables over here. Hence, we can apply the independency, the conditional independency over here, to turn this term into a product term of n equals to 1 all the way to n, and individual conditional probability of xn condition upon wn over here in this particular term here, where now we say that the Markov random field prior, or the pairwise potential, is actually given by this prior term of w1 all the way to n over here. So in this case here, because we have the prior knowledge as mentioned in the previous slide, that we want to encourage the neighboring pixels of the clean image to take the same label as much as possible, and hence we can model this into our Markov random field prior terms over here using the pairwise potentials. For each one of these random variable of wn over here, we are going to consider all its nearest neighbor, or the neighbors that is in the clique of the wn over here, denoted by n, where n and n over here, they all belong to the same clique. We are going to form all the pairwise potential in the Gibbs distribution over here. We'll see that two models later, the Ising model or the Potts model, which can be used to model the smoothness between neighboring pairs of latent random variable in the clean image, where we want to give a higher cost to this, or a lower probability value if both of them are taking different labels, and we want to give a higher probability value if both wn and wn are going to take the same label. The second term over here, which is the likelihood term that we're interested in, it's also otherwise known as the unary potential, where in this case we are simply going to model this as a Bernoulli distribution. So suppose that condition upon the case where wn, our latent random variable that corresponds to the observed random variable of xn, equals to 0 over here, then we are going to assign it a probability of rho over here. And in the case where the latent random variable is equals to 1, we will assign it a Bernoulli distribution of 1 minus rho. So what this means is that we want to encourage w over here to take the same label as the observed random variable of xn over here in the Bernoulli distribution. So we know that Bernoulli distribution is just a two-state distribution, where this Bernoulli distribution here is going to represent the probability of xn condition upon wn equals to 0. This is because we want to encourage both of them to take the same label. So in the case where we know that we are assigning wn equals to 0, then xn better be in the same observation as wn to have a high probability value. And if xn is taking the opposite label as wn over here, then it has to have a lower probability value. And we'll see that in the case where we condition upon Wn equals to 1, then these two probability values would have to flip direction. This means that in the case where we want Pxn condition upon Wn to be equals to 1 over here, then the higher probability of 1 minus rho over here, which we have assumed to be higher, we have assumed that 1 minus rho is more than rho over here in this particular, the first instance over here, then we would have to swap the relation over here, because in this case this would be representing 0 and this would be representing 1. So in the case when we know Wn equals to 1, then xn taking the value of 1 should have a higher probability than xn taking the value of 0 over here. And hence this is described by this unary potential in terms of the Bernoulli distribution in these two equations over here. Now we'll apply the maxima a posterior inference on the posterior distribution that we have defined earlier on for the Markov random field. And in this case here, we'll see that our objective is actually to find all the latent random variable, the states of the latent random variable, which we denote as W1 to Wn here, where we want to find the optimal value such that we maximize the probability of the posterior distribution. And by applying Bayes' rule on this guy, which is what we have seen earlier, we'll end up with the likelihood term over here, as well as the prior term over here, which we saw that this prior term is going to become is denoted by a binary potential cost function, as well as this likelihood term over here. It's going to be denoted by a unary potential term that we have seen in the earlier slide. And note that the normalizer after applying the Bayes rule is removed from here. This is because the normalizer is actually a function of xn, which is independent of w that we want to optimize over. Hence this particular constant can be removed from the optimization algorithm here. And the next thing that we do would be to apply the log on the Bayes rule. After we apply the Bayes rule, we apply this log function over here, such that we can change the product term into a summation term here, where we'll end up with this particular expression over here. Then evaluating this particular term here, the prior probability term here with our binary potential distribution that I have mentioned earlier on here, we will get this particular term here, where we can enforce the smoothness prior constraint on our optimization over here. And what this means is that we want all the neighboring pixels to take the same label as much as possible. The next thing to do here would be to change the maximization into a minimization, or the negative log posterior distribution here, by simply applying a negative throughout this probability distribution over here and changing the argmax into a argmin. So the reason why we want to do a argmin instead of a argmax over here is that as I have mentioned in the start of the lecture, that we will solve this inference, this MAP inference, using the Maxflow min cuts algorithm, which is actually a cost function or a optimization solver that is used to solve the discrete optimization problem. So usually in optimization, we will say that we'll do a minimization instead of a maximization. Hence, to keep the terms inconsistent with the Maxflow min cuts algorithm, we'll change this argmax into argmin by simply applying the negative log posterior operation here. And then the last thing that we do would be to replace this likelihood term with our unary potential function that we saw, that can be described using the Bernoulli distribution in the previous slide. And the objective now would be to simply minimize this total cost function, which is given by a set of unary terms that tells us how compatible the data. This means that all my observation of x1 to xn we want it to be as compatible to all the labels of 1 to n that we assign to the latent random variable over here, as well as it also has to fulfill the compatibility of the neighboring labels given in our prior distribution. This means that we want to also enforce that all the latent random variable, or each one of these latent random variable, to be taking the same label as their immediate neighbors that are forming a local cliques in the graphical model. Here's an example where we only consider a pairwise smoothness potential. This means that there is no observation, there's no x over here in this particular graphical model. And now we can see that this particular 4-node Markov random field is given by the probability. The joint probability is given by this particular term over here, where we simply write the probability of W1 all the way to W4, and that's given by the Markov random field of the pairwise potential of 1, 2, between 1, 2, 2, 3, 3, 4, and 4, 1 in this random field over here. And let us assign some values to this particular binary cost function that we have, or binary potential that we have over here. So since we said that we want neighboring pixels, or those that are in the clique, to take the same label as much as possible, what this means is that for any neighboring pairs of pixel over here, W1 and W2, or in more general term, we talk about the neighboring pixels of Wn and Wn over here, we want both of them to take the same label as much as possible. Since we are talking about the binary labeling problem, W is going to take a state of 0 or 1, and we want it to be as smooth as possible. This means that for neighboring pixels of 0, 0 and 1, 1 over here, we want it to have a high prior probability, smoothness prior probability. Hence we assign the value of 1 over here. And in this case, it's a potential. That's why we can assign any number. It need not sum out to 1 over here, since there's a partition function that will do this role. But what's interesting here is that since we want to enforce pairwise smoothness, this means that if the two neighboring pixels of Wm and Wn, they are not taking the same labels, for example in this case here 1, 0, then we will penalize it by giving it a low probability value or a low potential over here. We will simply make 0, 1 as 0.12 to make it take a low potential value or a low probability value. Now what's interesting here is that since we have defined in the previous slide here that we have only defined the potentials for a local potential. This means that we only define these 4 states over here, the 4 different potentials over here. For the case of a binary potential of Wm and Wn, where there are n and n neighboring pixels over here, we can see that by putting this back into the probability distribution here, which actually represents the graphical model or the interaction between 4 different pixels over here, we can see that the end result of the joint probability of PW will also tell us that we are going to penalize neighboring pixels from not taking the same label, and we are going to reward or give a high probability value to neighboring pixels that are taking smooth or the same pixel label. We can see an example here that if all the latent random variables over here, W1 to W4, follows the same state, 0, 0, 0, 0, then this would be the most smooth possibility, where we are going to give it the highest probability value among the all. And there's actually another combination where we can see that when W1 to W4 all takes the same state of 1, then we'll see that these two actually have the same probability value over here. And what's interesting here is that the more the number of the random variable taking the same state, the higher would be the probability. And it's also important to note that the probability distribution here needs to be computed by summing all the values and normalizing it over this particular sum of all the values, which is the partition function over here. And if we were to randomly sample from this joint probability distribution of W1 all the way to Wn over here, by simply defining the local potential probability to be smooth. This means that I'm going to define this Wm and Wn according to what we have seen earlier in the 4 different states. And by putting this back into the joint probability distribution of all n number of pixels over here, and we are going to sample one particular state or 4 different particular states over here from this joint probability distribution. We can see that here's 4 examples of 4 different samples that we sample from this joint probability distribution that is defined using the pairwise potential that we have defined earlier on. And in this case, we can see that these 4 potentials these 4 probability distribution of the states of W1 to W2 and all the way to Wn over here, we can see that it's actually mostly smooth in the region where all the black regions over here, they are very smooth. In the case where it's white, it's also very smooth. You won't see any salt and pepper noise over here. This shows the effect of having a pairwise smoothness. Now, having defined the negative log posterior where we can find the optimal W's over here, W1 all the way to Wn over here, which is equivalent to minimizing the unary potential and the binary potential terms that we have defined earlier on. The next question is how to optimize this particular cost function, and we'll look at how to make use of the graph cut algorithm to minimize this particular cost function over here, such that we can get the optimal W's for the latent random variables to recover the clean image. And we'll see that there are 3 cases of graph cuts over here. In more general terms, over here is that in the case of the image denoising, the binary image denoising, we will have the MRF type. This means that the latent random variable W's over here is going to take a 0, 1, a binary state, and if the case is submodular, then we will see that exact inference is going to be possible. As well as if it is a binary random variable, this means that W takes 1 out of K state, and as well as it's submodular, then we will also see that exact inference is possible. In the case where it's taking a multi-label and non-submodular, then we will see that approximate inference is possible by using the alpha expansion algorithm, and this will only hold for some cases. Now, we'll look at the more specifically on what's graph cut, and we'll see that graph cut simply means that this particular cost function over here can be converted into a graph problem. So notice that note that this particular graph problem that I'm talking about here is not the graphical model problem that we are talking about. It's just converting this into a graph, and we are going to perform graph algorithm on this particular problem. Here, in particular, we are going to look at the max flow or the minimum cut algorithm on a graph, and we'll see that this can be this results in the solving of this optimization of this particular cost function here in a polynomial time. Now, before we look at how to solve the maximum a posterior problem with the max flow min cut algorithm, let's look at the max flow min cut problem in more detail and how we can solve this particular problem using the augmented path algorithm. It all originated from the height of the Cold War between USA and USSR. So the American scientists at that time, in the early 1950s, they thought of this free world goal, where the objective is that given the road network of USSR at that time, where we have St. Petersburg over here, which is a big city in USSR that is near to the coastal area. So what this means is that all the goods that is coming from the sea can enter the mainland of USSR via St. Petersburg here, where we can see this as the source all the goods, and especially the goods has to be transported into the capital city of USSR, which is Moscow. Let's say Moscow is somewhere here, which is inland of USSR, and this is often seen as the terminal city or the terminal node that we wish to transport the goods from the coastal area into the important cities that are inland of USSR at that time. And these goods would have to flow through the road network, which are connected by the important cities or important checkpoints that are distributed along the way from the St. Petersburg, the source, to the terminal node of Moscow over here. And now the question is that what is the minimum cuts, or what is the minimum number of connections of edges between any two checkpoint nodes in this road network that the Americans would have to destroy in order to completely cut the source from the terminal node, which means that by destroying all these edges, these links between the important checkpoints in the road network, the goods will be completely stopped from flowing from the source city, which is St. Petersburg, into the important city, capital city of Moscow in USSR. And this is also known as the minimum cut. This means that I want to cut off, or I want to destroy with the road networks with the minimal efforts that is needed to stop the flow from supplying from St. Petersburg all the way to Moscow. And we'll see that by doing this minimum cut is also equivalent to finding the maximum flow from the source towards the terminal nodes in the particular graph over here. So more formally, we can formulate the max flow min cut problem as the graph problem, where specifically we have a directed graph that is denoted by G, which contains a set of edges, Eij over here, denoted by Eij over here. These are directed edges with arrows pointing from one node to another, and a set of nodes which we denote as V1 all the way to Vn over here. And let S, which is the source node, which is a special node which we denote as the source node, be in the set of V, be in the set of all the nodes in the graph. And we'll also define another special node which we call the sync node that I have mentioned in the previous slide, which will denote as T, to be in the set of the nodes in this directed graph of G. And we'll further denote the flow through an edge by F of Eij. This means that there is a flow of F through the edge of Eij in the particular graph over here. And we'll also define the capacity of an edge of Eij denoted by U of Eij. And this means that it's the flow capacity from any two nodes that is linked by the edge of Eij. Suppose that I have the node of Vi and the node of Vj over here. And this is linked by a edge of Eij, a directed edge of Eij over here. So we can see this particular edge over here as a pipe, a one-directional pipe that is sending some flow of a fluid from the node of Vi into the node of Vj. And the amount of flow of this fluid through this particular pipe of Eij here would be denoted as F of E, I, and J. This would be the flow through the edge of Eij. And of course, each pipe over here would have a maximum capacity that it can fetch. This means that there is a limit to the amount of flow that can be sent through the edge of Eij from node Vi to Vj. And this particular capacity over here we will denote it by U of Eij. So what this means is that U of Eij would have to be more than or equals to 0, because it cannot be a negative capacity. It can be a zero capacity. This means that there is simply no edge between Vi and Vj. And in this case here, the amount of flow here would have to be limited by the capacity of the edge. This means that the flow over Eij will always be smaller or equals to U of Eij, which is the capacity over here. An example of this max flow mean cut graph, or the directed graph, would be given in this example, shown in this particular example over here, where it is a directed graph and that is made up of a collection or a set of edges denoted by Eij, where these are directed edges with arrows over here, and a set of nodes denoted by V1 all the way to V7 plus 2, where we have the source and the sink as well. And these numbers over here, that is the weights of the edge over here, would be the flow that we can send through. In other words, these are the capacity of the edge that we can send the maximum amount of flow from the source node to node number 2 here, for example. In this case here, the maximum flow that we can send through would be 10. Hence, the capacity here would be equals to 10. So this U of S and V of 2 would be equals to 10 over here. This simply means that the maximum amount of flow that we can send over Eij over here would be smaller than or equals to 10 over here. Now, we'll also define a cut in the graph. A cut is simply a node partition on the set of ST, such that the source will always be in the set of S, and T, the terminal, will always be in the set of T, where all the nodes that are in S and T, the intersection of S and T over here, is going to be a null set. This means that when we make a cut here, we are going to partition this particular graph into two disjoint sets of nodes, where the S union T would be the whole graph itself, and the capacity of S and T simply refers to the sum of the weights of the edges leaving S. This means that after we have made the cut into the set of S and into the set of T, it contains the source and it contains the terminal nodes in both S and T respectively. All the nodes that are contained in S, it better be disjoint set. It better be a disjoint set from all the nodes that are connected in T over here. And what's interesting here is that there should also be a connection between the set of S and T in the graph, because these are original graph. Both the set of nodes in S union T over here would have to form the whole graph, or the original graph itself. This means that there has to be some links between, or edges between, the two sets of nodes over here, and we are going to cut over here. And the cutting, or the cut of all the edges here, the sum of all the weights or the capacity of the edges over here would be what we call the capacity of the ST cuts that is leaving the set of nodes of S over here. And there are two examples that's shown here of a valid cut, where we can see that given this particular graph, which we have seen in the previous slide, a valid cut would be a cut here, that we can see that by doing this cut over here, the set of S, all the nodes that are in the set of S over here, in this case it would be just one node of the source over here, would be the intersection of this from all the nodes that are in T would be a null set, and the union of these two sets would be the whole graph itself. And what's interesting here is that we can also see that by cutting this, there won't be any way of sending any flow from the source to the sink anymore over here. And the capacity of this ST cut over here would be simply the sum of all the capacities of the edges that we have cut, which is 10 plus 5 plus 15. That gives us 30 over here. Here's another example of the same graph where we have another valid cut over here. We can see that it fulfills the definition of the cut or node partition of between S and T over here. We can see that these are the two sets which we call S and we call T over here. In the first set, it contains S. In the second set over here, T, it contains T, which is the sync node over here. And we can see that both the nodes in S intersect T is actually null set, whereas the union of both the sets are going to give us the graph itself. And this means that this fulfills the a valid cut property. And the capacity of this particular cut between S and would be the sum of all the capacity of the edges that is leaving the set of S over here. So we are only considering the arrows that are pointing out of S towards T as the capacity over here. And hence we are not considering this 6 over here, which is pointing the opposite direction from T towards S. Now, having defined what's a cut on the graph, the minimum cut problem is actually to find the ST cut with the minimum capacity. This means that there are many possibilities of cutting or doing a graph partition between the set of S nodes and the set of T nodes in any given directed graphs here. And now the question is that which one of these cuts has the minimum ST capacity over here, and that particular cut would correspond to our minimum cut solution. And obviously there might be more than one solution here. And what's interesting here is that we will later see that the minimum cut is equivalent to the solution of the Maxima a posterior problem that we are going to solve. And what's even more interesting here is that we'll also show that the minimum cut is equivalent to the maximum flow, where the solution can be found using the augmented path algorithm. What this means is that in order to find the Maxima a posterior solution, this means that we can directly use the augmented flow algorithm, which is equivalent to finding the maximum flow across the graph and to find the minimum cut across the graph. So now let's define the flow in a more formal way. As I mentioned earlier in the slides, that the flow is an assignment to the weights, so that the flow is always within the limit of the capacity from 0 to U, because we are looking at in this case here, we are looking at two nodes, Vi and Vj. We can think of the edge over here, Eij, as a pipe that is connecting the two nodes of Vi and Vj. And where the maximum capacity that we can send over from Vi to Vj over here would be U of Eij. And this is why it's natural that the flow, the amount of flow that we can send across, would be limited by the capacity of this particular pipe or this particular edge that is connecting Vi and Vj over here. And hence, and since this U over here, the capacity is always more than or equals to 0, this means that the flow must be always between 0 and the capacity of this edge over here. And another important characteristic of the flow is that it must follow what we call the flow conservation. This means that all the flows that is entering a certain node must exit that particular node in order for flow conservation to be preserved. This means that given the particular node of Vi over here, all the flows that is coming in from this particular edge must be equal to all the sum of the total flow that is coming out of this edge, with two exceptions, which is the source and the sink node, because the source node would be the one that is generating the flow, and the sink node would be the one that is taking in all the flows that are generated from the source node. And here's two examples of the to illustrate the two properties of the flow. The first example over here, we can see that that the blue numbers over here represents the flow, the current flow that is sent from the source towards the sink. We can see that in this case here, we are sending a flow of 4 along this edge, and the other two edges over here, there's 0 flow. So we can see that on the other end, following the flow conservation, that whatever that is generated, whatever flow that is generated from the source would have to end up in the sink. in this case here, it sums up to be 4. We can see that in this across at the sink end, the total sum of the flow that is flowing into the sink would be also 4 in this case here. And we can also verify that at any point or any node over here, the total flow that goes into that node must equal to the total flow that is coming out of that node. For example, in this case here, node number 3, we see that there are 3 flows going into node number 3, where 2 of them are 0 and 1 of them is 4 over here. And we can see that the total flow out of this particular node over here must be equals to 4, where there are actually 2 arrows that's pointing outward over here. We can see that one of them is 4, the other one of them is 0, and this adds up to be the total flow that is going into this particular node over here. And we can also see that all the blue numbers over here, which represents the flow, it has to be more than or equals to 0 and lesser or equals to the flow capacity. So we can easily verify this by looking through all the pairs of numbers over here. Here's another example of the flow that is going into the graph and coming out of the graph, where we can see that the total flows over here that is sent from the source is equals to 10 plus 3 plus 11, which is equals to 24. And we can also see that the total number of flow that is coming out, going into the sink, is also equals to 24 over here. Hence, the flow conservation is preserved. And we can also verify this in any of the nodes over here. So say, for example, 2 over here, we can see that there is one arrow that's pointing inward, which sends in a flow of 10. The total number of flow that's coming out following these 3 arrows over here would be 6 plus 0 plus 4, and that's equals to 10. And this means that the flow conservation property is actually obeyed over here. We can also easily verify from the pairs of numbers over here that the capacity property of the flow is also satisfied. Now we can see that from any given graph over here, there are many ways of sending flows across, as long as it fulfills the 2 properties of the flow and within the limit of the capacity of each edges over here in the graph. And the problem of finding the maximum flow simply corresponds to finding that particular flow out of this many possibility that maximizes the flow from the sink to the source. Here we can see that we will keep on increasing the flow from every one of this particular link that is linked to the source node, and there would be a limit of how much flow we can send across from the source to the sink, given all the capacities of the edges over here. And the problem is that we want to find the maximum flow that we can send across from the source node to the sink node. And in this example here, the maximum flow is equals to 28. We can actually verify this over here. So in this case here, 10 over here cannot be, the flow here cannot be increased because it has already reached the maximum capacity of this particular edge over here. And let's try by sending a flow of plus 1 over here, which is still within the capacity of this particular edge over here. And we can see that in this case here, the flow wouldn't be able to flow through here because 8 over here has already reached the maximum capacity of this particular edge. But we can still send 1 across from 3 to 4 over here. Hence, this will be plus 1. And we can see that this plus 1 here can also flow through this particular edge over here from 4 to 7. And this will become plus 1. But what happens here is that it will get stuck at 7 because we will not be able to send it across this node of this particular edge that links node 7 to the sink over here. And we can also verify that it's also not possible to send another additional flow over here. So in this case here, if we were to plus 1 over here, we can plus 1 in this particular edge that links node 7 to 4 and 4 over here, but we'll end up with the same problem that this plus 1 will not be able to send across this particular edge from 7 to the sink over here. Hence, in this case here, we will say that the maximum flow has been reached that we can send from the source to the sink of this particular graph over here. Now, having defined the flows and the cuts of a graph, we can make several observations. The first observation that we can make is that let f be a flow and let st be any st cut, which we have defined earlier on. Then the flow that is sent across the cut is equal to the amount of flow reaching t. So what this means is that if I have a flow over here, which is denoted by f, and that I send across from my source node across the graph into the sink over here. So this would be the total flow that I'm sending from the source towards the sink. And given any particular cut over here, for example, this particular cut represented by this blue line over here, I would be able to partition the graph into two sets of nodes denoted by S and T over here. And this would be my ST cut over here, denoted by this blue line over here, or this blue curve over here. What this means is that the total net flow that is sent across the cut it must be equal to the amount of the flow that is reaching T over here. So in this case, I'm sending a total flow of 24 from the source over here, which is 10 plus 4 plus 10 over here. Then the total flow that I have sent across the S and T, the sets of nodes of S and T, it better also add up to be 24 because of the flow conservation property that we have seen earlier. So we can verify this easily by looking at the total flow that is sent across from S to T is 6 plus 8 plus 10 over here, and that's equals to 24. And we can also see that this flow of 24, it better also go to the sink following the flow conservation property that we have seen earlier. We can also verify this. 6 plus 8 plus 10 over here is also equals to 24. The second observation that we can make is that let f be also the flow from the source and let st be any st cut. Then the value of the flow is at most the capacity of the cut. So what this means is that if I were to make a cut over here, for example, which partition this particular graph into two sets of S and T following this ST cut over here, then the maximum number of flow that I can send across from the set of nodes of S to the set of nodes of T, it better be well under the capacity of the cut over here. This means that whatever total capacity that I can have across this particular cut of all the edges that partition the set of nodes of S from T over here, the maximum amount of flow that I can send across would be limited by this particular capacity over here. So this is not surprising because following the properties of the flow that where we define that we have seen that earlier that the flow would have to be limited by this capacity of the edge, the maximum capacity of the edge over here. And this would also be similar here, where between these two sets of nodes, where we simply view the whole set of S nodes and the whole set of T nodes over here as one big node over here, and the total flow or the total capacity that links these two sets of nodes would be given by the total capacity of all the edges along this particular cut over here. The third observation would be we'll similarly let F be the flow and let ST be the ST cut, whose capacity equals to the value of F over here. And then what we can conclude here is that F over here would be a max flow and ST over here would be a min cut. So what this means is that given that we have partitioned the set of nodes in the graph into the set of S and T nodes over here, and all the links between these two sets of nodes over here of S and T over here, the cut over here, if I have the total number of flow that flows across from the sink, from the source to the sink node in the S and T sets of nodes over here, if this particular total flow over here is equals to the total number of capacity, so all the flow is equals to the total number of capacity of all the edges over here, then we can conclude that we have reached a max flow and a mean cut, and both of them are equivalent to each other. And so the objective now would become clear that we are after the max flow and mean cut, which is the same thing. This means that once we have found the max flow, we would also have found the mean cut. And this also gives a very strong clue on how to find the max flow and mean cut over here, where we'll simply send the flows across from the source to the sink until a point where we saturate the flow, and we'll find all the cuts of the edges along the edges where the flow is equals to the capacity. So here is an example where we will send the flow, total number of flow over, until we reach saturation over here. We can see that the maximum flow value is 28 over here. So we can verify this 10 plus 4 plus 14 equals to 28. And we can further verify that we can no longer send additional flows across any one of these edges over here that will reach the sink node over here. And in this case, we will have reached the maximum flow. And now, according to observation 3 over here, which is also the conservation, which also follows the conservation of flow from the source towards the sink of this set of ST nodes over here, we can conclude that but after we have found the max flow, which is by sending in all the flows until we reach saturation, we can find the mean cut by simply looking for the edges where the flows equals to the maximum capacity of those edges. And once we have found all these partition, all these cuts along these edges that fulfills this particular property, and if we can partition the nodes into the S and T partitions over here, then we can conclude that this particular cut over here is equivalent to the mean cut. Hence, this means that by finding the mean cut, if we want to find the mean cut, then the first thing that we need to do is actually to find the max flow. And once we find the max flow, is equivalent to finding the mean cut over here. Now, before we look at the augmented path algorithm to solve the maximum flow problem, and as well as the mean cut problem, because they are equivalent according to observation 3, let us first define the residual graph. So given a two-node graph over here, which is the original graph denoted by Vi and Vj over here, we've seen earlier on that in our definition that the flow across this particular graph of two nodes is given by this number over here, which is denoted by f of Eij, and the capacity denotes the maximum flow that can flow across from Vi to Vj, which we denote as U of Eij over here. And we'll now further define what is called the residual edge over here, where the residual edge is simply defined as the undoing of the flow that is sent from one node to another. So in this case here, the original graph simply tells us that we are sending a flow of 6 from Vi towards Vj over here. Now in the residual graph, we are going to undo this particular flow. This means that we are going to send the flow in the opposite direction from Vj towards Vi, and we are going to take the residual capacity by taking the difference between the original capacity of the graph minus away the flow that is sent across the graph, and in this case it would be 17 minus 6, and that would be equals to 11 that is written. And now it's important to note that in the residual graph, where all the edges represents the residual capacity, must have a strict positive residual capacity here. So what this means is that the residual capacity would have the same meaning as the capacity, that it must be strictly more than or equals to 0. Now we can use the residual graph to define what is called the augmenting path over here. And an interesting observation, which is our fourth observation in the graph algorithm, is that if there's any augmenting path that exists, then we have not yet reached a maximum flow. And we will simply equate the augmenting path to be the path in the residual graph. Here's an example over here where we have an original graph that looks like this, and here we can see that due to the capacity of all these edges, we can send a 0 flow in the first edge over here and a flow of 10 in the second edge over here. So this is a valid flow that we can send from the source to the sink of the graph over here. And here we can see that this 10, we can channel it towards here, and finally it flows back into the sink over here. So the total flow over here would be 10. And we can denote this, or we can convert this particular flow graph into the residual graph that we have defined earlier. So in this case here, we'll simply flip the direction of arrow when it's reached any particular edge over here, has the flow has reached its maximum capacity. So in this case here, we have 10 and 10 in this direction. The residual graph would be that in this direction over here, it would become 0. So we can omit this particular arrow and simply flip the direction of the flow, reverse the flow in the other direction of 10 over here. And in this case over here where there's 0 flow, we can see that the edge over here, the residual capacity will be simply the same as the original graph over here. Similarly, in this case here, it's the same. So after we have converted the original graph into the residual graph, we can see that according to the flow direction of the arrow, we can still send flows across this particular graph because there still exists a path over here where we can send the flow from the source towards the sink, where there is still enough capacity in all these edges for us to send a flow from the source to the sink. And since this path over here, which we also call the augmenting path over here, still exists, what this means is that this particular graph, this particular residual graph, has not yet reached a maximum flow. And what we can do here is that we can continue to send additional flow into this particular graph over here. So in this case, we can see that we can still send a flow of 4 over here, and it's still we can still manage to send this across the particular graph into the sink. And what's interesting here is that once we have sent this flow, after we have sent this flow over here, we can convert the original graph again back to the residual graph. And here we can see that at this stage over here, or this particular residual graph will show us that it's no longer possible to send any flow from the source towards the sink in here anymore. It's pretty much apparent over here where both the arrows are now pointing towards the sink. This means that there's no more augmenting path, and we can come to a conclusion that maximum flow has been reached in this particular graph over here. Now, the augmenting path algorithm to find the maximum flow across a graph can be summarized in this particular pseudocode over here. So we'll start off by sending a flow across the across the graph, and we'll convert this into an augmenting path or residual graph, where we'll find existing augmenting path in this residual graph. And while there's still an existing augmented path in the residual graph, we'll find the augmenting path and compute the bottleneck complexity of this particular graph, and we'll send the augmented flow across this particular lowest edge or the bottleneck capacity in this particular graph, as we have seen in the earlier example over here. So in this case here, we saw that we sent a certain flow that is saturating the particular path over here, which we then convert it into a residual graph where we can find an augmenting path over here. And in this case here, from this augmenting path, we will find the bottleneck capacity. What this means is that across this particular path that we have seen that still exists in this particular residual graph over here, we will check all the capacity of this particular residual graph over here, the augmenting path over here, and we'll find the bottleneck capacity, which is actually 4 over here. What it means by bottleneck capacity is the smallest capacity along this path. So note that in this particular example, there is only one augmenting path that is remaining in over here, but there could be more than one particular path over here. We'll just simply select any one of those and check for the bottleneck capacity, which is the smallest capacity of flow that we can send across this augmenting path over here. And in this case, it's 4. Hence, the next step, we will send for a flow of 4 across this augmenting path, and then we'll repeat the process until we find no more augmenting path, and we'll terminate the augmenting path algorithm, and hence we have found a maximum flow across the particular graph over here. So there's no one single way of finding the augmenting path, as I mentioned earlier, that after we have converted the graph into a residual graph, there might be more than one augmenting path that is available for us to choose from. So usually we'll follow 2 rules over here, either of these 2 rules. We'll select the paths with the fewer arcs for us to send to check for the bottleneck capacity in the next step, or which is easily implemented using the breadth first search algorithm, or we'll simply search for the path that is with the maximum bottleneck capacity. This means that the fattest path which allows us to send the maximum flow across from the source to sink, which we can actually use the Dijkstra algorithm or the breadth first search algorithm to search for this particular maximum bottleneck capacity. Now, as I have mentioned in the observation 3, once we have found the maximum flow of the graph from the augmenting path algorithm, that is equivalent to finding the minimum cut. And this is summarized in the max flow mean cut theorem, or otherwise known as the Ford-Fulkerson algorithm in 1956. Where it states that in any network, the value of the max flow simply equals to the capacity of the mean cut. This is where we have already seen from observation 3. And here's an example over here where after applying the augmenting path algorithm, we find that this is the maximum flow that can be sent across from the source to the sink of this particular graph. And the next thing that we need to do would be, according to observation 3, is that we need to find all those edges with the same capacity as the flow that is sent across from the max flow. And in this case here, we see that this is the 3 edges that we can find that where the number of flow that is sent across is equal to the maximum capacity of those edges. And by cutting across these edges over here, we would be able to cut or partition this particular graph into 2 disjoint sets of S and T, where the set of S contains the source and the set of T contains the sink node over here. And we'll according to the Ford-Fulkerson theorem over here, we say that this is equivalent to the minimum cut. So in summary, what we have looked at earlier would be the augmenting path theorem, where we say that a flow F is the maximum flow if and only if there are no more augmenting paths. And this means that we can use the augmenting path to find a maximum flow across the source and the sink of a graph. And once we have found the maximum flow or the max flow, we can see that this is equivalent to finding the mean cut according to the Ford-Fulkerson theorem or the observation 3 that we have seen earlier on. And this is also otherwise known as the max flow mean cut theorem that we have seen in the previous slide. We'll prove the augmenting paths and the max flow mean cut theorem simultaneously by showing that the following 3 properties are equivalent. So the first property here is that if F is a maximum flow, then the second property will also hold that there is no augmenting path relative to F. So this would be, by proving this particular 2 properties to be equivalent over here, we would have proven that the augmenting path theorem is true, such that the augmenting path, when there's no augmenting path, then we have reached a max flow. And this is actually equivalent to observation 4 that we have seen earlier. So where in the augmenting path algorithm, we say that if we haven't reached an augmenting path, or we haven't reached the state where there is no augmenting path, then it implies that the flow that we send across is not the max flow. And hence, this proves that 1 and 2 are actually equivalent. To prove 3 is equivalent to 1 is also easy. Which we have already seen it in observation 3, where if we partition the two sets of nodes into S and T cards over here, using these S and T cards over here, we have seen in observation 3 that this partition over here is equivalent to the min cut, where when the max flow across the source node to the sink node that is contained in S and T sets respectively has been reached. And this simply implies that there exists a cut whose capacity is equivalent to the value of the flow that is sent across here, and where F is a max flow over here, and this is exactly observation 3. So the last equivalence here is slightly more difficult to prove. We'll show this in the next slide, where we'll see that when there is no augmenting path relative to F, there actually exists, this implies that there actually exists a cut whose capacity is equal to the value of F, and this will establish the max flow min cut theorem, or the max flow min cut property over here. So in this case, let's do the proof using this graph over here, where let F be the flow with no augmenting path. This means that in this case here, the max flow has been achieved. This means that we can no longer send any flow from the source to the sink node in the particular graph. And S over here be the set of vertices reachable from S, the source node in the residual graph. As I mentioned earlier, that we are going to partition this into two sets, which is S and T over here. And we'll define capital S over here be the set of nodes that contains the source node over here. And since we have defined the source to be in the set of S, and there's no more augmenting paths that is from the source to the sink, what this means is that the sink node cannot be in the set of S over here, since there's no more augmenting path that is that exists in this particular graph over here. So what this means is that all the nodes that is contained in S, they are reachable from the source node over here. And since there's no more augmenting path that is connecting S to T, the source node, to the sink node over here, what this means is that there must exist a set of edges that leaves this set of S, or that connects the set of nodes of S to T, where we have partitioned it into these two partitions over here, such that it actually points from all the graphs, all the edges over here that connects these two sets of nodes, actually points from the set of nodes from T towards S. This means that we will fulfill this criteria, or this particular property, that all the nodes that is contained within S are reachable from S over here. So, and what it also means is that all the other nodes that are contained in T wouldn't be reachable to S, and this means that there won't be any augmenting path from that is connecting S, the set of nodes of S to T. And this also implies that the set of the node, or the sink node of T, cannot be in the set of S over here. And furthermore, this also implies that all the edges leaving S, the set of nodes of S over here in the original network, would have the flow equals to the capacity of the edge. And in order for this to happen, in order for us to be able to partition these two sets of nodes of S and T such that all the set of nodes within S is reachable from S, and the source and the sink node over here is not reachable from S, the source node over here. And this means that what we have established in the first bullet point over here is that all the arrows that are pointing, all the edges that are pointing from that are connecting the set of nodes of S and T, it must be pointing from T towards S. And what this simply means is that since this is the augmented path or the residual graph, what it simply means is that in order for this to happen, the arrow must have flipped completely in the opposite direction, where the maximum flow, where the flow must have reached the maximum capacity of that edge in order for it to flip direction. And the third point to be made here is that all the edges entering the S in the original network would have a flow of equals to 0. This is just simply to because that this part over here, all the arrows that are pointing already pointing from T towards S. This means that once this has been reached, once this state has been reached over here, then there won't be any flow that is flowing back towards the sink. Otherwise, the arrow would have been in this particular direction instead. And as a result, what we can conclude here is that the total flow that is coming from S towards T would be equals to the total capacity out of S. So we can see that all the flows that is going out of S, we sum it out, and into S over here would be equals to the total capacity out of all this set of nodes in S over here, and that would be equivalent to the capacity of the ST cut over here, since this guy here is going to be 0, because the third point over here simply states that there won't be any flow going into S, and the second point over here states that all the flows must come out from S into T over here, and that's going to be equals to the capacity following the conservation of the flow and the maximum capacity of the graph. Hence, as a result here, we would have proven that if there's no more augmenting path that connects the graph in the residual graph, then there actually exists a cut over here, which is equivalent to the maximum flow out of the source nodes in the particular graph. And this particular flow over here would be equals to the capacity of the edges over here and of the ST cut over here, and hence we can conclude that the maximum flow is equivalent to the minimum cut. So here's an example to illustrate the augmenting path algorithm to find the max flow and min cut, where we are given the 6-node graph where we have a source and a sink, additional source and a sink node over here. Each one of the capacity of the edge is denoted by the second number on the edge over here, and the first number here would denote the flow that we are sending across that particular edge. We can see that first we can send any arbitrary flow across over any one of these 3 edges. Suppose that we have found a path over here. We can find any paths on this particular that connects this particular source and sink nodes over here, and we'll find the bottleneck capacity over here, which is in this case is 4.1, because this is the smallest capacity along this particular path over here. So we'll decide to send 4.1 across, and then once we send 4.1 across, we will see that we will continue to search for the path, since there's a still residual or augmenting path that still exists over here. In this case here, we can see that suppose that this is the next path that we are interested in taking, and we can see that in this case here, we can get the augmenting path over here by simply finding the bottleneck capacity, and in this case the bottleneck capacity would be 1.3 over here, since it's the smallest capacity amongst all. And here we will continue to send 1.3 flow across this particular path, and now this flow over here would have reached 5.4. So the residual over here would be 2. This means that we can only send a flow of 2 over here, and we need to take this into account when we consider the next augmenting path. So we'll continue to do this that means that we'll continue to find the path and send a bottleneck flow across all the augmenting path that we can find until finally we can no longer send any flow across from the source to the sink node. In this case here, where we can see that we have reached the maximum flow. By sending any more flow over here, we will get stuck somewhere along the path, and we can no longer send this particular additional flow from the source towards the sink anymore. And in this case, we will terminate the augmenting path algorithm and conclude that we have found the maximum flow. And once we have found the maximum flow, the next thing to do would be to do the minimum cut, where we have proven in the previous that the minimum cut would occur at edges where the maximum capacity or the maximum flow has occurred and saturates that particular capacity of the edges. So in this case here, we can see that there are few edges where the maximum flow reaches the maximum capacity of the edge over here. And in this case here, we'll see that this can be cut. This guy here can also be cut, and this guy here can also be cut. This guy here and this guy here, where after cutting this, we found the mean cut. This means that we found the mean cut, and we can see that it's no longer possible to send any flow across from the sink or across the source towards the sink after we have found this particular mean.